Welcome to this explainer. Let's jump right in. Today, we're diving into exactly how DoorDash completely transformed their chaotic, siloed data pipelines into an incredibly unified powerhouse using OpenTelemetry. Honestly, it's a massive story of extreme scale, really smart engineering, and basically creating order out of pure data chaos. Here's our quick roadmap for today. We'll start with life before OTel, then unpack the Lego mental model and examine their 100 terabyte solution. From there, we'll look at building custom pipelines, controlling the log chaos, fixing edge visibility gaps, and finally, future-proofing at scale.
Section 1. Life before OpenTelemetry, the old, siloed reality.
Okay, so in the old world of fragmented infrastructure, things were, frankly, pretty chaotic. DoorDash had a stint with Flink for logs that really didn't go well. They had entirely separate pipelines for traces and these custom setups for events. If you wanted to support any new use case, you had to navigate completely different, highly specific protocols. If you've ever had to maintain totally separate code bases for logs, metrics, and traces, you know it inevitably results in working in silos and just highly stressful firefighting when something breaks. But moving to OpenTelemetry brought them a unified code base. With strict semantic conventions enforced across all telemetry types, the team now operates from a single mirror repository of the OpenTelemetry collector. This standardizes their data globally, drastically cuts down on the literal fires they have to put out, and keeps the engineering team highly motivated instead of constantly feeling burned out. Moving to Section 2, the Lego mental model, OTel collector basics. To really grasp this, you've kind of got to think of the OpenTelemetry collector literally like a giant set of Lego blocks. You can just snap together different receivers, processors, and exporters to construct these incredibly powerful, highly customized pipelines. It's a single binary capable of processing all your telemetry types, logs, metrics, and traces. You receive the data, transform it, and export it exactly where it needs to go. The true power here is the modularity. Because you can swap out any single block without tearing down the whole structure, you completely eliminate vendor lock-in. If you decide you want to change where your logs are stored tomorrow, no problem. You just swap out the exporter block. It is a crazy flexible system. Section 3, the 100 terabyte solution, handling massive scale. Okay, let's talk about the sheer, staggering scale here. Their unified pipelines process an absolutely massive 100 terabytes of log data every single day. Just try to imagine managing that kind of volume on a daily basis to support 3,000 engineers. It requires absolute precision, and the stakes for any pipeline failure are tremendously high. And the scale doesn't stop at logs. For traces, they hit an astonishing peak of over 15 to 18 million span requests per second. Literally millions of requests every single second. And finally, at peak capacity, they're pushing a staggering 5 million logs per second right through this system. To serve those 3,000 engineers seamlessly at that kind of velocity, the underlying architecture doesn't just have to be good, it has to be absolutely bulletproof. Section 4. Building custom pipelines, bridging the gap. So standard out-of-the-box tools simply weren't going to cut it for this kind of scale, right? So they went ahead and developed over 30 custom OpenTelemetry components. For example, they built a custom Kafka exporter because they needed to use a trace ID as a partition key to build a tail sampler, which is something the upstream client didn't even support. And if you're wondering why that matters, to make sampling decisions on a full trace, all the spans of that specific trace absolutely must land on the exact same processing node. They also built an S3 Parquet exporter for logs and a ClickHouse exporter using a super low-level library for critical performance. But here's the real game changer. Instead of just using basic mock functions for testing, they rigorously test these components by spinning up actual in-memory databases per test. It runs a transformation, inserts the data, catches those really weird, obscure bugs a basic mock would completely miss, and then destroys the database. It's an incredibly rigorous way to guarantee stability before the code ever hits production. The architecture for all this massive data flows in a highly reliable 5-step process. First, workloads like Java SDKs send data to the gateways. Second, these gateways, which are basically just custom OTel collector instances, transform the data. Third, they produce that data into Kafka clusters. Kafka acts as a massive shock absorber here. Fourth, on the other side, consumer OTel instances read from Kafka. And finally, those consumers route the data to its final destination or vendor. By strategically placing Kafka right in the middle of this flow, they ensure that if a final database goes offline, the data just queues up safely instead of vanishing into the void. Section 5. Controlling the log chaos. Strict volume controls. Now, even as their custom log router strictly enforces daily quotas and automatically downsamples noisy services, they provide one absolutely crucial, reassuring guarantee to their product teams. We never drop your error logs. They might give a service a quota of, say, 1 terabyte a day, and if breached, a control plane automatically downsamples them to protect the system without penalizing the services that are behaving well. But no matter what, critical error logs will always make it through for troubleshooting. It's really the perfect balance of strict system discipline and maintaining developer trust. Because, during real-world incidents like a rogue load test suddenly spamming a terabyte of logs an hour, the system has to protect itself. Their edge load shedding processor automatically drops a percentage of excess logs just to keep downstream clusters alive. By load shedding at the edge, dropping, let's say, 20% of the volume to safely process the remaining 80%, they protect their Kafka clusters from severe latency spikes and prevent total system outages that could be caused by just one noisy neighbor. Section 6. Solving edge visibility gaps, tracking external APIs. Okay, imagine you build a microservice API, right? Inside Kubernetes, it looks completely healthy. But out at the Cloudflare edge, your actual users are getting incorrectly blocked by bot protections upstream before the traffic even enters the DoorDash ecosystem. Your perfectly healthy pod will never see the traffic, leaving you entirely blind to the outage. Your service-level telemetry shows 0 errors, leaving you incredibly frustrated and totally unaware that your external API callers are failing. To fix this massive blind spot, DoorDash leveraged those OpenTelemetry Lego blocks we talked about earlier. First, Cloudflare pushes edge audit logs directly into an S3 bucket. That action immediately triggers an SQS message, which essentially tells a custom OpenTelemetry receiver, hey, pull these new log files into the pipeline. Next, a custom processor reaches out to DoorDash metadata to precisely match those logs to the specific internal endpoint the blocked call was originally meant for. Finally, it exports that enriched data over to Grafana. Now, product teams can set up super accurate alerts and see exactly when their upstream customers are failing, allowing them to troubleshoot the problem immediately.
Finally, Section 7. Future-proofing, evolving at scale.
To eliminate manual bottlenecks going forward, their immediate roadmap includes automating Canary rollouts because doing that analysis manually just leaves way too much room for human error. They're also generating automated CI integration tests. Importantly, they are heavily focusing on back pressure management. Back pressure essentially means that if a destination, like ClickHouse, goes down, the system naturally slows down accepting data at the source rather than processing all those messages entirely, only to drop them on the floor later at the exporter level. And finally, they're pushing for dynamic feature flags, meaning they won't have to completely bounce their 190 different deployments just to load a new configuration. So the absolutely crucial takeaway here is that transitioning to unified, standardized pipelines unlocks unparalleled scale and deep developer visibility. By adopting this Lego block approach with OpenTelemetry, DoorDash managed to tame an unfathomable 100 terabytes of daily logs while maintaining extreme precision and reliability. Think about how these unified architectural principles could apply to your own setup, which really leaves me wondering, how is your own team managing observability chaos at scale? Thank you so much for joining me for this explainer, and keep exploring.